Good afternoon, ladies and gentlemen. This particular video is going to focus on something that was not on the original sheet for rotational motion, but it's something that once you work with it, you'll be like, oh yeah, this makes a ton of sense. So we're going to talk about the idea of the center of mass of something, all right? And in fact, this lab has two names. The first is called finding the center of mass, or it's also referred to as the balancing point. We're going to see why that is as we go through this lab. All right. Now you notice that this sheet has a bunch of questions on it. In fact, what I want you to do, if you could, is unfortunately we would do this lab in class. We can't do it right now. So instead, what I want you to do is I want you to kind of pause this video in a second, which I explain what you're going to do. But what you're basically going to do is you're going to take a ruler, if you have one at home, a meter stick, a flat piece of wood. Honestly, anything that can be used as some sort of seesaw. All right. Then you're also going to try and find in your house, apartment, wherever you may be, three masses. Make sure that two of them are either the same thing or the same mass. All right. So honestly, you can just eyeball it if you think you have two things that are pretty similar. And what you're going to end up doing is you're going to basically go through and you're going to be balancing these objects on this meter stick, ruler, whatever you're going to use. All right. And your goal is to hopefully kind of balance these out so that you can see where you put them and where you need to put your finger to balance it. Okay. So you're going through and answering these questions. They're pretty self-explanatory. In a second, I'm going to go through and I'll just talk about briefly the answers because honestly, the thing that I'm much more interested in is the center of mass, defining what it is. All right. So if you can, follow directions, answer these questions, go all the way to the end. There should be a line and then underneath it says center of mass formula. You're going to stop there. All right. So pause the video at this point, go through the lab, and then we'll come back and talk about the answers and talk about center of mass. All right, so ladies and gentlemen, hopefully you had a chance to play around, make things balance. I know that you'll have plenty of experience from the number of times I've seen you balance things in my classroom when we weren't talking about center of mass. So with that being said, all right, hopefully for some of these that ask you to give the position, if you don't have a measuring utensil, it's gonna be kind of difficult, but you can kind of eyeball where it should be. And honestly, the first one, and I'm going to talk about reference a meter stick because that's the lab I did it with, so. But it's all going to be kind of the same depending on what you use. So I'm starting by just balancing the meter stick on its own. Probably you found that the meter, just the object you used is the balancing board. The balancing point is going to be placed pretty much in the middle. All right, on a meter stick it would be 50 centimeters. Now, if I put these two masses on there and I take two of them at the same mass and I put them on the meter stick, depending on what you did, if you got it to balance again, more than likely you had them both be the same distance away from the balancing point. So let's say you had the balancing point is at 50 centimeters, you put one of those masses at 30 centimeters, which means it would have been about 20 away. The other one also had to be 20 centimeters away, which means it would have been at 70 centimeters. Okay? Now, if you just put that third mass on there, like the next question asks, and you don't move the other ones, there's honestly only one spot you can put it that won't cause it to tip over. Otherwise, what will happen is that if you put it anywhere but the middle at 50 centimeters, it'll cause that seesaw, meter stick, whatever, it'll cause it to start rotating the way that both the more mass is. Okay? So, the only way to get it to work, and answers the next question, figure out how to balance it with three masses, the only way to get it to work is to honestly put that third mass on the balancing point. All right? And we're going to find out that there's a reason that makes sense and it works for us. So the next one is I wanted you to arrange your masses in new positions so that they're balanced again, so that you can still balance it at 50 centimeters. Okay, and honestly, there are a ton of different combinations. No combination is right or wrong. It's really all about just getting it to balance. So honestly, that one just comes down to figure out what it looked like and just kind of visualize what happened. Okay. Now, if you played around with the masses several times, you've probably observed a couple things. One of the things you might have observed is that depending on where you put the masses affected how much they want it to kind of flip over. Okay? And one way you can see that is that if you kind of put a lot of mass on one side and you put one on the other, you had to move the one that only had one mass. You had to move it much farther out so that it could balance out the two that were more massive. Okay, and if you didn't try that, try it again and see. Put one mass close to the center, put two masses close to the center, and see what you have to do to the one mass in order to get it to balance out. All right. Now the next piece is I wanted you, in this time, I wanted you to put masses at specific points, and I wanted you to try and figure out where the balancing point is. Because what we're going to find out is that there's two different things you can do to get something to balance. You can either move where the masses are on that object and make sure it stays at a specific point, or the other thing you can do is you can change where you're going to balance it and pick specific points to put your masses. All right. And once again, this answer can kind of be different depending on what masses you pick, but you probably got that you are going to have a balance point that is closer to 55 or 67 centimeters than the 7 centimeter one. Okay. Now, the last piece, I want you to once again move the masses around. This time you have two masses at 7 and 15 centimeters and one at 85 centimeters. Once again, if you don't have a meter stick or anything, just do your best to kind of eyeball what that should look like. And then you probably found that the new balance point was going to be closer to the 7 and 15 centimeter side than the 85 centimeter side, which nicely answers the last question for this little lab. Is the balance points closer to the one mass or two same masses? It's going to be closer to the two masses than the one mass. All right. And the reason is because of what we're about to talk about, which is referred to as the center of mass. So, the center of mass is kind of a concept that a lot of you have probably kind of dealt with before. We're just going to define it in a very specific way. So a center of mass is basically whenever I have a system that has a lot of different masses in it, we can actually reimagine them acting as one bigger mass. All right, just like we like to do in physics, we hate having a bunch of small things. We like to imagine it as one simple thing. All right. Now, the place where all of the masses are balanced is referred to as the center of mass. All right, and the reason is because that is the point where all of the mass acts like it's sitting. Okay? So, I can take a lot of different masses and put them on a meter stick, but the center of mass is going to be the point where if I hold it up with just my finger and I put it at that spot, it will stay perfectly balanced because my finger is acting like it's supporting all of the mass. Okay? Now, the center of mass is a very specific formula that we can use. And honestly, when you get to higher level center of mass stuff, you're going to use calculus and use integrals. For this class, we have a very specific formula we use for a very specific kind of situation. So what it looks like is the following. And what it basically says is that the center of mass position, that's what that XCM equals, is going to be determined by two things. It's going to be determined by the sum of the masses times their positions. So what that means is that on the top row, you're going to take every mass that's in the system, you're going to multiply that mass by where it is, and then you are going, at least in one dimension, and then you're going to add up all of those calculations together. And we're going to practice it in a sec to show what I mean. Then, once you have that all added up, you're going to divide the system by all of its mass. And what's left over is the center of mass position. Okay? Now, to show this, let's do an example. So I want you to use this formula to prove that if I set up a 1 kilogram, I have three 1 kilogram masses, and I put them at 35 centimeters, 65 centimeters, 50 centimeters, and they're all sitting on a 50 gram meter stick, that the center of mass of that whole system is still going to be 50 centimeters. All right. Now, the first thing we want to do is identify, we just want to tell ourselves, all right, how many objects are in the system? All right. I know I have three 1 kilogram masses, so I know I have at least three objects, but the catch here is that the meter stick also has mass, which means we also have to pay attention to that object as well. All right, so we're going to end up having four objects. So XCM is going to equal the mass times the position of all four objects. So we'll start with the 1 kilogram objects. They have pretty simple ones. The mass is 1 kilogram, so it's just 1 kg, times its position on this meter stick. So it would go from 0 to 100. So the first position is going to be, at least the way I've set it up, it's going to be 35 centimeters, so 0.35 meters. Okay. Then next, that's the first one. We're going to add it up. We're going to do 1 kilogram, all right, times 50, because one of them sitting in the middle, it's 0.5 meters, plus 1 kilogram times 0.65 meters, plus, to finish it up, the mass of the meter stick, which is 0.05 kilograms, times its balancing position, or where its center of mass is. And this is actually an interesting thing. When you have a system that might be composed of small objects like these little masses and a big long object like this meter stick, what you do is you reimagine that long object like the meter stick, you reimagine it as all of its mass is at its center of mass. Okay, so what that means is that in this case, for that 50 gram meter stick, the center of mass is going to be at 50 centimeters. So that's going to be where we say its mass position is. All right, so 0.5 meters. Now, right there, we have the entire top row. All right, and what we do is multiply all those things together, and we do our multiplication and then add them all together. Gotta follow some PEMDAS. And then once we have that, we should have some number on the top. Now, the next thing we do is we just add up all the masses that goes on the bottom of this. So it's going to be 1 kilogram plus 1 kilogram plus 1 kilogram plus 0.05 kilograms. All right, so the total mass is going to be 3.05 kilograms. All right. And then if you go through and you make that calculation, what you're going to find is that it says XCM is going to be equal to 0.5, which is exactly what we expected. That's where the balancing point was when you did this. It's right in the middle of the meter stick. All right. So that's how we're going to use this formula for center of mass. All right. Now, we have two example problems on this that we can also go through as well. And in fact, I am going to stop this particular video right now just that I can focus on these two questions and not have to rush through them. So the second part of this video is going to cover these two example problems for finding center of mass. Okay, so I'll see you there in a sec.